Hello, this is Professor Keen, and this is a continuation of my lecture on Chapter 16 of A Student's Guide to the Great Physics texts. We're talking about syringes, siphons, and suckling infants. So the main idea here is that a lot of the kinds of effects, such as suction cups sticking to surfaces and wine not pouring readily out of a cask unless there's a hole in the top, a lot of those kinds of effects that had been previously attributed to the idea that nature abhors or avoids a vacuum, as far back as the time of Aristotle, but going up to the time of Galileo, a lot of those kinds of effects, Pascal is arguing that they can better be understood by understanding that the air itself has weight. And so we've been talking about some of those things in detail, and as I mentioned in the last lecture, I wanted to talk about how siphons work. Pascal mentions that the function of a siphon can be understood using the idea that air has weight. So that's what I'm going to detail this time. This actually might be broken up into two separate lectures, depending on how fast I can go here. But in order to maybe give some background on how siphons work, what I'd like to do is explain about how high water can get pumped up in a tube. So what I'm going to do is I'm first going to draw a glass tube. This is an imaginary glass tube. It's imaginary because I'm imagining it to be very, very long. And you'll see why I'm going to do this in a moment. So suppose we have a bucket like this. And let's suppose that this bucket, let me get my color scheme here. This bucket is full of water. Okay, so here's water in it. And this tube is sticking out of it. And I say it's an imaginary bucket because I'm imagining that an imaginary tube. It's so long that it sticks out of the top of the Earth's atmosphere. Okay, so you might imagine that out here is the vacuum of space. Okay, and in here we have air, and then down here we have the surface of the Earth. So this is imaginary. You can't really build a glass tube that long, but you'll see why I'm doing this in a moment. So the question is how high, if you either have this going up to space, to the vacuum of space, so there's a vacuum in here, or alternatively, you don't have it as long, but you hook it up to a vacuum pump so that you get a vacuum inside of this tube right here, how high can water be pumped up in a tube like this? Or rather, the better question to ask is how high does the weight of the air push it up, right? Because the idea that Pascal has been arguing is that this atmosphere over here has a certain height. This is the height of the air on this side, and that is many miles high. And it has some weight, so it pushes down on the surface of the water with some force. And of course, inside of here, there is no air, and so there's no force pushing down, so there's an unbalanced force. This air can push the water up. But it only pushes up a certain height. And how high does this get? Let me use an orange marker as well. How high can it get? Well, on this side, right here, this indicates the height of the water inside of there. This is the height of the water. And one can experimentally find this. The maximum height of the H2O is right around 31 or 32 feet. I'm just going to write 32 feet. That's the maximum height that by evacuating this tube or making it go all the way up to space, the vacuum of space, that's the maximum height the water will go up, because at that height, we're saying 32 feet of water has a sufficient weight to balance as many miles of air as the atmosphere is thick. Okay, that's the idea. Now let me say one other thing. Let's suppose we had another bucket, and this was also resting on the surface of the Earth. And I'm going to continue to draw the atmosphere across here. And we were to have another tube. So let me get rid of a little bit of that. So have another tube going all the way out to outer space. The main point being that the tube has a vacuum in it, if that could be said. And now this bucket, instead of water, let's suppose that we put liquid mercury in this bucket. So now this is mercury, whereas this one over here was water. So we already said that the atmospheric pressure can push 32 feet of water up. How high can the atmospheric pressure, which is the same in this case as it was in that case, this is the height of the air or the atmosphere, how high can it push the mercury up in the tube? Well, you might guess it's not going to push it up as far, and that's because mercury has a much higher density than water. So how high does it push it up? Well, the maximum height that it can push it up, right here, the height of the mercury, and we want to guess what it is? The height of the mercury is about 76 centimeters, or 760 millimeters. And that number, perhaps if any of you are into meteorology, that might be a familiar number to some of you, because we sometimes say that the atmospheric pressure is 760 millimeters of mercury. And that means that our atmospheric pressure, that is the weight of our atmosphere, is able to support a column of mercury that's 760 millimeters tall. And so sometimes you'll hear the relationship that 1 atmosphere of pressure is the same as 760 millimeters of mercury. It's a claim about how tall a column of mercury can be supported by the weight of the atmosphere. Okay, so that's by way of background. Now, the main point we want to talk about is how do siphons work? So what I'm going to do is I'm going to draw a siphon. I'm going to describe this qualitatively first, and then I'll probably stop, and then in the next lecture I'll give a more quantitative explanation of how siphons work. So let's do this. Let's say we have the ground, and let's say we have a platform on the ground like this. And then we put a bucket of water right here. So I'll have a bucket and another bucket down here. And then we put a siphon going from one to the other. Okay, and as I said, we're going to imagine that there's water in here and there's water in here. And provided we prime this siphon, that is, we fill it with water initially. You know, you could take this glass tube and you could put it under a pool of water and fill it with water and then quickly turn it upside down and put the ends into these buckets. And if you were to do that, you would notice the siphon works. That is, the water is going to go from this direction to that direction. It's going to siphon the water from the high level to the low level. And the question is, why does this work? Why does a siphon water from a high level to a low level? And how does Pascal explain this? Well, as you might imagine, he says it's because we live under an atmosphere of air. Okay, so let's talk about why that can explain how a siphon works. And I'm first going to explain how it leads to a bit of a paradox, but then we can resolve the paradox. So here is the somewhat confusing thing to start out with. So on this side, we have the surface of the water has a certain height. I'm going to say the height of the atmosphere on the left side, or above the left bucket, is there. And here, I'm going to draw another arrow. This is the height of the atmosphere on the right side. And you might see where I'm going with this. The difficulty that immediately arises is if the atmosphere on this side is weighing down on the surface of the water and trying to push it up like this, and if the atmosphere on the right side, this column of water, is weighing on the surface and trying to push the water up like this, well, which one is going to be pushing harder? It seems immediately that the one on the right-hand side, that's under a taller column of air, so to speak, would have a larger weight of air pushing down than the one on the left side. Because after all, the right bucket is lower than the left bucket, so the right bucket has more air, more weight of air pushing down and trying to push the water that way. So you might think, wait a minute, shouldn't the siphon work in this direction? That's a confusion, right? Why isn't it pushing it that way? Well, as it ends up, it doesn't push it that way. We know that. It pushes it this way. So how can we understand why the siphon pushes the water in that direction? Well, here's the way that Pascal proposes to solve this issue. We have to think not merely about the weight of the air that's trying to push it, but we have to think about the weight of the water that is trying to counteract the pushing. So here's what I'm going to do. Let me erase these for a minute to get these out of the way. Go like this. So what I'm going to do is I'm going to imagine dividing the siphon into two parts. Okay, so I want you to think about the left part. This is the left side of the siphon. And I want you to think about that separately from the right side of the siphon. So let's think for a moment about the left side of the siphon. Well, you have this force that's trying to push down on this side due to this column of water. So that's the force due to the air on the left side. That's trying to push it up this way. But on the other hand, you have this column of water and the weight of that's trying to fall back down or push in this direction, right? So that's the force due to the water on the left-hand side. All right. And as long as this is less than 32 feet of water, then the weight of the air can push it in this way, right? There's going to be an excess of force pushing it up compared to the weight pushing down. After all, that's what we had talked about over here, right? So the air has enough weight to suspend a 32-foot column of water. So if, let's say, over here you only have, let's say, 1 foot of water, then the atmosphere has more than enough weight to push 1 foot of water up. What about the right-hand side? Well, on the right-hand side, you have this entire column of air that's weighing down on this side and trying to push this water up here. So there's a force due to the air on this side. But on the other hand, this region of water right here is trying to weigh down and push down this way. That's the force of the water. So there are these competing forces on here, one trying to push this way and one trying to push this way. And over here, there's competing forces, one trying to push this way and one trying to push this way. And here's the point that Pascal makes. Although the weight of the air is higher, let's suppose, for example, that this height is an extra, 6 inches. So there's an extra 6 inches of air trying to push this water up that way compared to the left side. But there's also an extra 6 inches of water that's trying to fall down. And that extra 6 inches of water is more than enough to overcome the extra 6 inches of air. And as a result, there's a net force that is pushing water in this direction. So that's how the siphon works. And this is Pascal's explanation of the siphon, and I should probably stop there. And what I'm going to do next time is go through some of exercise 16.4, where I give a slightly different explanation than what Pascal did, but allows us to have a quantitative understanding of how the siphon works. So